Variable acceleration. So whenever the acceleration, the value of the acceleration changes, we can apply calculus to solve for the displacement, velocity, and acceleration, right? When you see questions like these, we'll do some questions like these just now. You see what I'm talking about? When are we required to use calculus in order to find displacement, velocity, and acceleration? We'll do questions like those just now. So going from displacement, which is usually denoted by S, sometimes you may see X as well. So going from displacement to velocity, we actually differentiate. So let's say you're given displacement. So I'm given S, and they ask me to find V. So V, how is V equal to S? Well, like I said, from displacement to velocity, we differentiate. So V is actually ds on dt, which makes sense because going back to our basic definition of velocity, velocity is the change in displacement, but the rate of change of displacement, right? So ds on dt. Then going from velocity to acceleration, we also differentiate. So we are given velocity and we ask to find acceleration. How is the acceleration and the velocity related? Well, differentiate. So acceleration is dv on dt. And it makes sense because our definition of acceleration is the rate of change of velocity. When we are doing rate of change, we said whenever we see the word rate, we know it's with respect to time. And what quantity are we measuring with respect to time? Velocity. So it's dv on dt. Do you understand that? Yes, nice. Where did everyone else go? There it is. Okay, so acceleration is dv on dt, v is ds on dt. But you can also say, so for acceleration, you can also say, or acceleration is actually equal to the second derivative of this. It's d2s on dt squared. And it makes sense because if you look at this diagram right here, displacement to velocity, we differentiate. Okay, we just did that. V is equal to ds on dt. If I want acceleration and they gave me velocity, I differentiate. A is dv on dt. But if they gave me displacement and I want to get the acceleration, there's no need for me to find the velocity and then differentiate again to find the acceleration. Why? Because if you looking at the diagram, this is ds on dt. So from this jump to this jump is ds on dt. But if I differentiate again, is d2y, give me d2y, d2s on dt squared is the second derivative. From here to here is the first derivative. Let me use. From here to here, that's the first derivative. So ds on dt. But if I want to go from here to here, I'm saying that there's no need to go get the velocity and then get the acceleration. I could actually make a jump from here all the way to here one time. The only thing is, if here displacement of velocity is ds on dt, so the first derivative, then from the displacement to acceleration is ds on dt, and then another one. So it's d2y, why am I saying y? d2s on dt squared. Do you understand that? Yes, no? Please repeat. Repeat what? Repeat which part? Derivative notation. Which one? All of them? Yes. Cool. Variable acceleration. Variable acceleration meaning that my acceleration is not the same. The value of acceleration is actually changing. You'll see questions like that in the past papers, right? And we'll see exactly when we need to apply calculus in order to find these quantities: displacement, velocity, acceleration. If you are given displacement and asked to find velocity, say jumping from here to here, we want velocity, we are given displacement. What is the relationship between v, velocity, and s, displacement? Well, it's actually ds on dt, differentiated, right? ds on dt. And it makes sense because our definition of velocity is the change in displacement on time. So let me just say the rate of change of displacement. When we did rates, before we started kinematics, we said the word rate implies with respect to time, hence the dt. And what quantity are we measuring with respect to time? Displacement, and the displacement is denoted by s. So v is ds on dt. Sometimes you might see displacement denoted by x. Doesn't matter, right? Just know v is ds on dt. You might see x, dx on dt, right? Do you understand that? Okay. And then if they gave me velocity, so before they gave me this, right? And they asked me to find v. But what if they gave me v, so my velocity, and asked me to find acceleration? So I'm going from here to here. According to this right here in this diagram, I need to differentiate. So I'm given v, and I want a. Differentiating, this would be dv on dt. And back to the definition of acceleration is the rate of change of velocity. The word rate implying with respect to time, hence the dt. And what quantity are we measuring with respect to time? It's velocity. So dv on dt. Do you understand that? Say if a question gives displacement, we differentiate to determine the velocity. And when we do the second derivative, we are finding acceleration. Yes. Okay, what I was saying just now, but based on what you just said to me, you understand what's going on. But just in case, I can kind of just came in, so I'll do it again. If I'm given displacement s, and I'm asked to find the acceleration a, technically you could find velocity first, so v is ds on dt, so find the first derivative, okay, and then using my value for the velocity, I can differentiate again to find acceleration. But that's a lot of work. Who wants to do that? Why would you go, so you see this red arrow, why would you jump from here to here, having to find this value, then you go from here to here? I mean, why? I mean, it's still correct, but yeah. I can just say the relationship between s, displacement, and a, acceleration, so this jump, is the second derivative. So d2s on dt squared. Do you understand that? Oh wait, hold on, I'm not seeing this. Okay, great. And how do we write second derivative? V is equal to ds on dt. Is it dv on dt or is it d2s dt? What are you talking about? Because I just saw the message. I don't know what you're talking about. How we represent the second derivative? It's easier in the chapter. I now understand that the notation is different based on what is given. Yeah. So we'll do questions like these, right? So you'll see exactly what I'm talking about. Yeah. So what if instead of getting displacement and having to find velocity, or getting velocity and I have to find acceleration, or given displacement and I have to find acceleration, whatever it is, right? Whatever combination. What if they give me acceleration and they ask me to find the velocity? So they gave me acceleration. So let me just write it on the right hand side. And they asked me to find velocity. How would I do this? Well, looking at the diagram, to go from acceleration to velocity, let me just draw the arrows. So from velocity to acceleration was differentiation. So let me just put a capital D. But that's not what I want, right? In this case, I was given velocity and asked to find acceleration. So I differentiate, hence the orange arrow labeled D. But if they gave me acceleration and asked me to find velocity, notice that this green arrow is going in the opposite direction of the orange arrow. And what's the opposite, or what's the reverse of differentiation? It's integration, because integration is an anti-differentiation process, meaning that it's the opposite of differentiation. These arrows tells me, this arrow tells me that it's the opposite of differentiation. This arrow is going up, this one is coming down. This green arrow is the opposite of the orange arrow. What is the opposite of differentiation? It's integration. So given velocity and you're asked to find acceleration, we would actually be finding the integral with respect to time. So V is the integral of A dt. Do you understand that? Cool. And same thing. If I'm given velocity and asked to find displacement, going from displacement to velocity, differentiation. But that's not what I want to do. I'm given velocity and I want displacement. Notice this arrow is opposite to this arrow. What's the opposite of differentiation? It's integration. Therefore, I want S, I'm given I'm given V. How do I do that? I integrate. So it's the integral of V dt with respect to time. You good with that, right? Both of them? Yes, okay, nice. Well, that's all you're required to know, right? That's all you're required to know in order to apply calculus to kinematics questions. And we'll practice them just now. So just keep that in mind. You need to know this. I actually told you this before, that when you see a particle is at rest, is there a second? No. Well, no. We're not getting into that. You're just required to know from this to this, and from this to this. Okay? Are you good with that? Note, when a particle is at rest, then v is equal to 0. We said this already. I put it in one of the earlier slides. When you see the word rest, or you might see instantaneously at rest, which means it's at rest, then the velocity is 0. And we just found out using calculus that velocity is actually ds on dt. Let me just go back. Velocity said when we are given s and asked to find v. So I want v, so I put it on the left hand side. I'm given s. We said v is ds on dt. So if when I'm at rest, my velocity is 0, and now I know that velocity is also the same as ds on dt. So if velocity is 0, that means that ds on dt must also be 0. Do you understand that?
Yes, miss.
Okay. Pause for questions. Doesn't that mean v? Okay, doesn't that also mean v, which is equal to the integral of a dx is, well, it's dt, yeah, is also 0? Yes. So if you see a question like that, yes, my velocity is 0, so whatever velocity is equivalent to, so like you just said, the integral of a with respect to time, put it equal to 0. You see questions like that, you see what I mean, right? Actually, let me just show you a quick example of that. So we just said at rest, v is 0. V is 0. But v is also equal to ds on dt. So if v is 0, then ds on dt has to be 0 as well. But we also know that v is the integral of a dt. So technically, this has to be 0 as well. Because if this is equivalent to velocity, and my velocity is 0, then this integral should also be equal to 0, right? Let's just say we're given limits. So they gave me an upper limit and a lower limit. So let me just call this T2 and T1. They gave me values for time, and they asked me to find the acceleration between T1 and T2. Let me just draw. This is just a random thing, right? This is actually one of the things here. Let me say this is T1 and this is T2. So maybe your question looks like that, right? I find the integral of this. So when I find the integral of my equation given, well, my expression of a, let's just say I get, let me make up something. Please let me know if I'm confusing you, right? We're gonna do a question like this, but I just want to show you what I mean before. Say we're given a is what, 3t cubed minus 4t squared. Just doing something easy, right? Minus t. I want velocity, so I know I have to find the integral. V, the integral of this will give me t minus 4t cubed and 3 minus t squared on 2. My upper limit, my lower limit. Okay, that doesn't make sense. Hold on, let me not put the upper and lower limits. Actually, no. Let me not try to give you an example because I'm going to mess it up if I create an example and the numbers don't work out. We have a question like that. Please do not panic. If you're confused, it's okay. We're going to do a question like that, and then you could ask me questions if you don't understand what's going on, right? Because if I make up an example and then the numbers don't work out, then you might get confused. And if you get confused, that's not a good thing. Those are all past paper questions. Yes, it is. Differentiated to get acceleration. Differentiate what to get acceleration? The example. Okay, let's not use that example because the numbers might not work out and then you might get confused. But there's a question similar to that. We're gonna do it just now. Let me just go through constant acceleration now. So before, just now, we're talking about variable acceleration. We use calculus and all that. What if my acceleration is constant? If I have a constant acceleration, I can actually use the equations of motion. So there are 5 equations of motion, and if you have a constant acceleration, you could actually use any one of these to find what you need. So let's say this first one, right? They gave you the final velocity v, they gave you the initial u, they gave you a constant acceleration a, and they asked you to find t. Well, I just substitute all my values into this equation to find the value of t. We are going to do questions on that. Please do not panic. We need to practice it, right? Okay. And oh my, you commonly see application of this right here. So these equations, when you given a velocity time graph, you would see what I mean. Those equations, you don't cram them. That's why you don't cram the equations. You need to actually understand how each one of these are derived to prevent cramming. You know, who wants to memorize these things when you could understand the derivations for each one of them? So it wouldn't really be memorizing since you understand what's going on, right? So I'm going to show you the derivations. Okay, so like I was saying, when do you have to apply these equations of motion? I said when the acceleration is constant. And you would see this when you're given a velocity time graph and the graph is actually a straight line. Let me try to do an example for this one. So let's say this is my velocity time graph. I'm just making up something. V, this is T. And they want me to find the acceleration of this line. We know from the key features we're required to know for velocity time graphs. That's a straight line. The gradient of a velocity time graph is acceleration. So if they told me that this velocity right here at this point is 20, we know it comes down to the y-axis. So, I mean, it comes back down here. So it's at rest, v0. Let's say the time taken is 4. They asked me to find A. What's the acceleration? I know this is a constant acceleration. How do I know that? Well, it's a straight line. A straight line has a constant gradient. Acceleration is my gradient, so therefore it's a constant acceleration. I could then substitute these values into my equation of motion to find t. Why am I able to do that? Because acceleration is constant. So v, my final velocity, is 0 because it starts here at this point and it ends down here, and my velocity is 0. So v is 0. U is the initial velocity. The velocity I start with, that's 20 on top here. Plus A is what I want to find. And T, how long did it take me to get from this point to this point? Well, they told me it's 4 seconds. So 4. And then you would actually find the value of A. So this is minus 20 is equal to 4A. So therefore, A has to be equal to -5 meters per second squared. And don't panic about the negative sign because the gradient of this graph would be negative. How do I know that? It's a downward slope. Then my value for A, which is the gradient, would also be negative. All that means it's a deceleration, which is a negative acceleration. We learned that when we were doing the definitions. A deceleration, the definition of a deceleration or retardation is a negative acceleration. So the value of my acceleration is negative 5. All that means it's a deceleration, meaning that my velocity decreases. And you could see it here, right? It goes from 20 to 0. Makes sense. Can we use the gradient method there also? Yes. Yes, you can. They're actually, let me not go there yet. We're going to do the past papers just now, and that's actually the second method, right? So you can use the equation of motion to find A, or you could just find the gradient. So it's actually 2 methods to do questions like these, right? Like I said, when we saw the past papers, you would see that. Okay, now these derivations. The meeting is gonna end, so just rejoin, right? But I'm gonna show you the derivations for all of these. And that's it for all the theory. We're going to do past papers. Simple so far. Well, yeah. It doesn't really get more difficult than this. So you're good. Okay, we're going to end this. Rejoin, right?